throughout your course in chemistry, you will be concerned with the nature of matter and the changes which matter undergoes, along with the reasons and explanations, insofar as they are known, for these properties and changes. Therefore, we might begin with a brief discussion of the classification of matter. On the board, you see a diagram illustrating one method for classifying matter. First, matter is subdivided into two broad categories, homogeneous and heterogeneous matter. Homogeneous matter is the same throughout. Properties of one portion of it will be the same as properties of another portion. Heterogeneous matter is not the same throughout. One portion will have one set of properties, another portion may have other properties. Now, homogeneous matter may be still further divided into solutions and substances. Solutions are of great importance in chemistry and will be considered in great detail later on in the course, so we are not going to spend any more time on them today. Substances may in turn be subdivided into elements and compounds. Elements are substances which cannot be decomposed any further by ordinary chemical means, and compounds are substances which are always composed of two or more elements united in a fixed proportion by weight. And when two or more elements combine to form a compound, the properties of the original elements disappear, and the new compound, with characteristic properties of its own, appears. Now, examples of elements are such materials as iron and copper and carbon and oxygen, and many compounds also are known to you, such as sugar and water and salt. Mixtures differ from compounds in that while they contain at least two or more elements or compounds or both, in the mixture each element or compound retains its original properties. And therefore the mixture has more than one set of properties. In fact, it has one set for each component. And the mixture can be made to exhibit these different sets of properties, and this is often of use when the mixture must be separated into its components. In this film, we're going to study the properties of two elements, iron and sulfur. We're then going to study the properties of a mixture of these two elements. And finally, we're going to study the properties of the compound which is formed when these two elements are united. In my hand, I have a small piece of sulfur. You should note that this sulfur has a yellow color, and you will have to take my word for the fact that it has no odor. Sulfur is hard, but rather brittle, as can be seen when I strike it with a hammer. In this test tube, we have placed some distilled water. Here is a lump of sulfur, which I've removed from this bottle, and we will drop the sulfur into the water. You note that it sinks, indicating that sulfur is heavier than water, or more dense, and that it does not appear to dissolve. In this test tube, I'll place another lump of sulfur, and to this sulfur add some carbon disulfide. We will now stir the sulfur in each tube for about 5 minutes. After about 5 minutes, we see that the sulfur in the test tube with the water has not changed its appearance at all, and can be considered to be insoluble in water. However, the sulfur in the test tube with the carbon disulfide looks much different than it did before. The large lump of sulfur has disappeared, and only a few fluffy particles remain suspended in the solution. The sulfur may be recovered from its solution in the carbon disulfide in this fashion. First, we will filter the solution containing the dissolved sulfur to remove any traces of impurities. we will permit the filtrate, which you can see is perfectly clear, to run out onto this watch glass. Then we will permit the solution on the watch glass to evaporate to dryness. After all of the carbon disulfide has evaporated, the sulfur has been redeposited on the watch glass in crystal form. Sulfur is hard, as it was originally. I think perhaps you can see the gleams of light from the crystal faces. This is a good example of a physical change, since the sulfur has been recovered after going into solution in essentially its original form. Some elements are attracted by a magnet, while others are not. When we apply the magnet test to sulfur, we find that the lump of sulfur is not attracted by the magnet. This is one more physical property of sulfur, which we will make note of for future reference. Since sulfur has shown to be insoluble in water and is more dense than water, a simple method for determining the density of sulfur suggests itself. On this balance, we're weighing a piece of sulfur. The sulfur weighs 38 grams. In this graduated cylinder, we've placed exactly 25 milliliters of water. And I'll now carefully slide the 38-gram piece of sulfur down into the graduated cylinder. The combined volume of the water and the sulfur is now 45 milliliters. And since we originally placed 25 ml of water in the graduated cylinder, it's easy to see that the volume of the sulfur must be about 20 milliliters. Density, which is a specific physical property of the substance, is defined as the mass of the substance divided by its volume. For sulfur, the weight of the piece of sulfur we used was 38 grams. And this mass or weight of sulfur occupied a volume of 20 milliliters. In carrying out the obvious calculation, we find that the density of sulfur is 1.9 grams per milliliter as determined by us experimentally. When we examine the chemical properties of an element, one of the properties that is usually examined is the reaction, or lack of it, of the element with acid. In this test tube, I will place a piece of sulfur. And then we'll add some concentrated hydrochloric acid. In the case of sulfur, no reaction takes place. Sulfur then does not react with concentrated hydrochloric acid. In this test tube, I've placed several pieces of sulfur, which we will heat in the flame of the Bunsen burner. Note that the sulfur melts rather readily, indicating that its melting point is not too high. You should also note that near the melting point, molten sulfur is a mobile liquid with rather low viscosity, and it is yellow in color. Now, as we heat the melted sulfur to a higher and higher temperature, you can see the color becoming progressively darker, and also the liquid becomes much more viscous. In fact, at this point, the sulfur moves very sluggishly in the test tube. And if we go to a little higher temperature, we find that we can scarcely pour the sulfur from the test tube at all. This is unusual behavior because most elements become less viscous as they are heated, while sulfur goes through a maximum viscosity peak at a temperature well above its melting point. Next, we will test in order to see whether sulfur burns in air. In a brass spoon, called a deflagrating spoon, we've placed 2 lumps of sulfur. We'll place the spoon in the flame of the Bunsen burner, cause the sulfur to melt, and to ignite. And I think you can see the blue flame with which the sulfur burns in the spoon. This is an important chemical property of sulfur, its ability to combine with oxygen by burning. We will now proceed to tabulate some of the physical and chemical properties of sulfur which we have just observed. The color of sulfur was yellow. Brittle? Yes. Soluble in water? No. Soluble in carbon disulfide? Yes. Reacts with hydrochloric acid? No. Product of the reaction with hydrochloric acid obviously doesn't apply. Attracted by a magnet? No. Density? 1.9 grams per milliliter. Burns in air? Yes. Melting point? Low. We now turn to the consideration of the properties of another element, iron. As an example of iron, we will use these small nails. We note that the color is silvery and metallic. Nails, of course, are well known to be hard, but they are not brittle, as sulfur was, as they can be rather easily bent. This property of strength with the ability to be bent is called malleability and is a characteristic of the element iron. Also, nails, in contrast to sulfur, are attracted by the magnet. Iron is one of the few elements that is attracted by a magnet. So rather quickly, we've developed several physical properties of iron in contrast with those of sulfur. In the 3 test tubes on the screen, we've placed 3 samples of iron. 2 of the samples of iron consist of iron nails. The 3rd sample is iron powder. Now to the tube on the extreme left, we're going to add some distilled water. And we see that iron is more dense than water, appears to react with it very slowly, if at all, and certainly does not dissolve. To the tube in the center, we're going to add some carbon disulfide. And again, the iron does not react with the carbon disulfide at any appreciable rate. This, you remember, is different than in the case of sulfur, because sulfur dissolved in carbon disulfide. To the tube on the extreme right, we will add a few milliliters of dilute hydrochloric acid. In this case, a vigorous reaction occurs. The gas is evolved. We will invert a 2nd test tube over the reaction tube and collect a portion of this gas. We will then test this gas with a burning splint to see if it might be hydrogen, because hydrogen explodes when ignited. Obviously, the gas was hydrogen and is a product of the reaction between iron filings and hydrochloric acid. we may calculate the density of iron by the same method that we used to calculate the density of sulfur. We have weighed out 94 grams of iron nails. And these 94 grams of nails have been placed in this graduated cylinder. In this cylinder, we've placed exactly 25 milliliters of water. And we'll now add the water to the nails in this cylinder. The combined volume of the water and the iron nails is now 38 milliliters. The density of the iron nails may be calculated using the same formula that we used for the density of sulfur. Our nails weighed 94 grams. The combined volume of the nails and the water was 38 milliliters. We had 25 milliliters of water to start with, therefore 13 milliliters represents the volume of 94 grams of nails. And the density of the nails is found to be 7.2 grams per milliliter. We will test the behavior of iron at fairly high temperatures by inserting a nail into the flame of this Meeker burner. You should observe that the nail soon glows a bright red color, but that it does not melt or burn at these temperatures and under these conditions. The properties of iron may now be placed on our table. Color was silver. Brittle? No. Soluble in water? No. Soluble in carbon disulfide? No. Reacts with hydrochloric acid? Yes. Product of the reaction? Hydrogen. Attracted by a magnet? Yes. Density? 7.2 grams per milliliter. Burns in air? No. Melting point? High. On these small pieces of aluminum foil, we've weighed out 4 grams of sulfur and 7 grams of iron. The reasons for these proportions will become apparent later in the semester. And we're now going to prepare a mixture of iron and sulfur. We'll grind these two powders together in this mortar. And this will give us a material, grayish in color, which appears to be homogeneous. It is not, however, since mixtures of iron and sulfur actually contain thousands or millions of small particles of iron and of sulfur separately. We'll now place a portion of this mixture in the test tube and treat it with some carbon disulfide. We're doing this in order to see if the properties of the original sulfur have been altered by mixing the sulfur with the iron. Because, as you'll recall, we found that sulfur alone dissolves in carbon disulfide. In the test tube, we have our carbon disulfide solution of what we hope is the sulfur and the iron in the mixture. We'll filter the solution to remove the suspended iron and catch the filtrate on a watch glass exactly as before. We will then allow the carbon disulfide to evaporate. After the carbon disulfide has evaporated, we see that we have a deposit of crystals of sulfur entirely similar to that which we obtained when we treated pure sulfur with carbon disulfide. Obviously, the properties of the sulfur have not been altered by mixing them with iron. We will now examine the mixture a little further to see if the iron has retained its properties in the mixture as well as the sulfur. I'll place a portion of the mixture in this test tube and add a few milliliters of dilute hydrochloric acid. You'll recall that when we did this with pure iron, hydrogen gas was obtained. Invert the test tube over the reaction test tube in order to catch any evolved gas. We'll permit the reaction to proceed for just a moment. You'll recall from our previous experience that sulfur does not react with hydrochloric acid, and I believe you can see the scum of sulfur that's floating to the surface here. The reaction between the iron and the sulfur is taking place at the bottom of the tube. We'll now test the gas in the tube by lighting it. And once again, the explosion indicates the presence of hydrogen. The properties of the iron have not been changed by mixing it with the sulfur, therefore. In the preceding experiment, we saw that when hydrochloric acid is added to the mixture of iron and sulfur, hydrogen gas is evolved. In this experiment, we will examine the properties of this gas a little further. In this test tube, we placed a small sample of our iron-sulfur mixture. In this test tube, we've placed some cadmium sulfate solution. The choice of cadmium sulfate for the reagent will become obvious later. Now I'm going to add some dilute hydrochloric acid to the iron-sulfur mixture. And cause the evolved gas to bubble into the cadmium sulfate solution. And I think you can see that very little is happening. We have previously studied the properties of iron and sulfur separately, and we then studied the properties of the mixture of iron and sulfur. We're now going to heat this mixture of iron and sulfur to cause these two elements to react chemically to form a new compound called iron sulfide. I've placed some of our iron and sulfur mixture in this test tube. We will now heat the test tube in the flame of the Bunsen burner. Heating is necessary in order to raise the iron and sulfur mixture to a sufficiently high temperature to cause the reaction to begin. Once the reaction starts, however, it gives off considerable heat and proceeds without further heating. Now, the reaction has started. You can see the bright red glow caused by the intense heat given off by the reaction. This then is an exothermic reaction, or a reaction which gives off heat. Don't be confused by the fact that we had to heat the mixture to cause the reaction to begin. This simply was necessary in order to achieve a high enough temperature to cause the reaction to start. Once the reaction did start, plenty of heat was produced to keep it going. In order to recover our new compound of iron sulfide, we have kept the test tube very hot, and we will now quickly thrust it into this beaker of cold water. The glass breaks, and our iron sulfide is now on the bottom of the beaker. We will remove it from the beaker and examine both its chemical and physical properties. Having examined the solubility of iron and sulfur in carbon disulfide, we now wish to test the solubility of our iron sulfide compound in that solvent. Here's a small piece of the iron sulfide which we've just made. You can see that it's hard, black, solid, obviously insoluble in water. We'll place it in this test tube and then add some of the carbon disulfide. We'll now wait about 5 minutes in order to give the iron sulfide a chance to dissolve, and we'll then filter as before. After 5 minutes, we will filter the solution and then evaporate the carbon disulfide filtrate. After the carbon disulfide has all evaporated, the watch glass has this appearance. You will note the complete absence of the yellow crystals of sulfur, which were so obvious when free sulfur was dissolved in the carbon disulfide. The sulfur in the iron-sulfur mixture has obviously been converted into a form in which it is now insoluble in carbon disulfide. We will now calculate the density of our iron sulfide by the same method that we have previously used for iron and for sulfur. A sample of iron sulfide has been weighed out and placed in the graduated cylinder. This sample weighs 12 grams. In this graduated cylinder, we have 25 milliliters of water. Add the water to the graduated cylinder containing the iron sulfide. Agitate to remove a few bubbles, and note that the volume of the water in the cylinder is 28 and a half. This is the combined volume of the water and the iron sulfide. The density of the iron sulfide may now be calculated as before. The mass of our iron sulfide was 12 grams. We found that this occupied a volume of 3.5 milliliters. Since the total volume of water and iron sulfide was 28.5 milliliters, and we had used 25 milliliters of water. Carrying out the division, we find that the density of the iron sulfide is 3.4 grams per milliliter. When we test the iron sulfide with the magnet, we find that it is completely unaffected. And this is in marked contrast to the properties of the original iron. Obviously, the magnetic properties of the iron have been destroyed when the iron was transformed into iron sulfide. When we reacted iron with hydrochloric acid, we observed that the gas hydrogen was produced. We should now perform the same test on our iron sulfide. In the test tube, we've placed several pieces of the iron sulfide, which we've just prepared. And to this iron sulfide, we'll add some dilute hydrochloric acid. Obviously, a gas is being produced. And we will replace the delivery tube and pass this gas into our solution of cadmium sulfate. The gas that's produced when hydrochloric acid reacts with the iron sulfide reacts with our cadmium sulfate solution to produce an instantaneous yellow precipitate. This is a much different reaction than we obtained when hydrogen was passed through cadmium sulfate. The formation of this precipitate is a good test for the gas hydrogen sulfide, which is produced in the reaction between iron sulfide and hydrochloric acid. Finally, we may place the properties of iron sulfide on our chart. Its color was black. Brittle? Yes. Soluble in water? No. Soluble in carbon disulfide? No. Reacts with hydrochloric acid? Yes. Product of this reaction? Hydrogen sulfide, H2S. Attracted by a magnet? No. Density? 3.4 grams per milliliter. Burns in air? No. Melting point high. We saw earlier that properties of a substance are the characteristics by means of which we recognize, describe, and differentiate it from other substances. In this experiment, we have examined the properties of iron in the form of nails and of sulfur. We have seen that these two elements retain their individual properties when they are combined in a mixture, but that when the mixture is heated, a chemical reaction takes place, producing a new substance, iron sulfide or ferrous sulfide. And in ferrous sulfide, the properties of the original iron and sulfur have disappeared, and a new substance with new properties has appeared.